x minus 8. And then if I want the critical numbers, I have to set the first derivative equal to 0. And look at me, my max, mins, or points of inflection occur. Where they occur, the x values, right? Not what they actually are. So 0 equals 2. And then I can take x minus 4 when I take the 2 out. And then I just solve this. This is all grade 11. We're going back to grade 11. Do I have to do the 2? Is it going to get me anything? No, it has no variable. So I'm just going to go x minus 4 equals 0, x equals 4. So that's my critical number. Critical number means something's happening there. Yeah. Yeah, it's illegal. Quadratics, whenever you want to solve a quadratic, you move everything to one side, set equals to 0.
Okay. And then you can't do it like normal algebra.
You can't do it like normal algebra.
Why is it illegal?
Because if you divide the x over, you've just created yourself, you've given yourself an NPV, and you're not actually solving. You still have an x left behind.
You're not dividing the x over. You add the 8 over and divide.
Sure, in this instance you could. If it was a linear, you could do that. The chance of you getting a linear, even from a quadratic, is going to be... Well, you could do it here, but the chance of you even giving you a quadratic to factor and get a critical number of is going to be not going to happen. They're usually going to give degree 3 or higher. Okay, I just picked this one because it was easier, and we kind of can see that for this one it's easier to figure out what your maxes and mins are because it's the quadratic. You have either a max or a min. You don't have options, right? So this one, is it concave up or concave down? It's concave up because I have a positive, right? So I know my graph is concave up. So I know x equals 4 is actually a what? It's a minimum. Don't know why I just put in brackets, but I did. It's a minimum. But that's just where it occurs. How the heck would I find out what the actual minimum is?
Plug it back into the original.
Plug it back into the original, always, because I want to coordinate off the original. So I'm going to do f of 4, which is 4 squared minus 8 times 4, which is 5, 4, negative 16. I just found the minimum without my calculator and without having to do completing the square. So if you actually understood derivatives, this is a lot easier than completing the square, but you'd have to understand derivatives in order to do it. So what do I want you to do? I want you to put the original on your calculator into your y equals and the first derivative into your y equals, please. So first derivative into y1, or sorry, first equation into y1, first derivative into y2.
Oh, hello.
That's when I think they let the things come down. In the cafeteria. Big seat. Good? Yeah. Okay. So the original is x squared minus 8x, and the first derivative is 2x minus 8. Okay. All right. So critical numbers of the first derivative are really just the x-intercepts, aren't they? Correct? So if you look here, my x-intercept is at 4, and on my first derivative, or on my original, my minimum is at 4. Do you see that? So wherever your x-intercept is on your first derivative graph, you could just draw down or up and find your min or your max, right? Or your point of inflection type. Now this is also something to note. These have tangent slopes, so it would be, this is also below. You see this? It's below the x-axis. The graph is actually decreasing here. And then these, which we're going to learn not today. And then these ones are actually above the y-axis, and the graph is doing what? Increasing on that side. So your first derivative will also tell you where it increases and decreases. Not today. I'm just showing you that that's what happens. Okay? So what you need to understand today is how do you find the first derivative and then get critical numbers. Okay? All right. Number 2. You're going to try this one on your own. We're going to still stick with polynomials. So say I give you x to the 4 minus 2x squared plus 1. I want you to get me the critical numbers. Okay, so we have f prime of x equals 4x cubed minus 4x. The great thing about most of these is that a lot of the time they'll just make it so you can have a GCF. You don't have to do synthetic division, even if it's a cubed or 2 or 4. So this one you could just, you're going to set it equal to 0, and we can take out a 4x. And then we're left with x squared minus 1, which we have to recognize as what? Difference of squares. So we get 4x, x plus 1, x minus 1. And then x equals 0, and then plus or minus 1. Okay, can you type the original in? And can you type the first derivative in? Why am I struggling to say first derivative? Type the original in and type the first derivative in. The original and the first derivative in. Now, look at the critical numbers. Shh. Look at the critical numbers of the first derivative. The critical numbers of the first derivative are the what's?
X-intercepts.
The x-intercepts. Yeah, on the first derivative. To see and compare. So, I have x to the 4 minus 2x squared plus 1. And then in this one I have 4x cubed minus 4x. That is not right. Pardon? Okay, so if we look at the critical numbers, I'm going to zoom in a little bit here. I'm going to go... If I look, the cubic one is obviously the first derivative, correct? Because it drops by 1 degree every single time you take a derivative of something. So a 4th degree will always be the original, then the 3rd would be the first derivative. What would be the second derivative? X to the 2. It's going to drop a degree, right? So if I look here, my critical numbers of the 3rd degree are here, here, and here. And what do they correlate directly with? The first one's a minimum, the second one's where the maximum exists, and the third one's where the min exists. Now this is what I told you to look for as well. Where this graph is below, where the first derivative graph is below, the original is doing what? It's decreasing. So the graph is decreasing here, and then the graph is decreasing here, correct? It's so tiny that it's causing a problem. And then this is above, this red, and it's increasing here, and then this above is increasing here. So it's where they decrease and increase. Like I said, we're not as concerned about that today. We're just connecting the two. We're really just concerned about critical numbers. Okay. How would I find the max and mins? I'd have to know where it's increasing and decreasing to get a max and min. Right now, all I'm getting is critical numbers, and sometimes that's all they ask for. It's just the critical numbers of the first derivative. Okay? 3. Now we're going to do this one. Four minus root x. So still a nice one to get a derivative of. F prime of x equals what? What happens to the 4? Goes away. This is just negative x to the half, correct? So what's it going to become?
Negative 1 half x to the negative half.
Negative 1/2 x to the negative 1/2. Now, critical numbers can also be the non-permissible values of the first derivative as well. And why is this one going to have a non-permissible value? Because the square root and there's a negative exponent, and so it's going to drop to the bottom. So technically, I could write it like this. Negative 1/2 root x. Could I not? Now, we did this in 30-1. Now you can see why 30- every single curriculum you do, every single one is done for a reason for the next one. So in 30-1, we talked about rational expressions, and we talked about when there's x in the denominator, they can't equal 0, right? We also talked about radicals, and we talked about whatever the heck's under a radical has to be greater than or equal to 0. We agree? And then I gave you a question in operations where I made you do a composition of a function, and I made you put a radical into a rational. So it caused you to have a radical in the denominator. Then you had to put your two rules together. What were the two rules if you had a radical in the denominator? Your rational, that your x can't equal 0, correct? And your radical is that what? It has to be greater than or equal to 0. But because it's in the denominator, what is it actually going to have to be? So my domain of this function of the first derivative is going to be, they don't ever do set notation, I don't know what, greater than 0. So I know that this function, when I go to graph it, is going to start at 0 with an open dot and carry on. Okay? All right. So the only critical number I would get here is, even though this is in the denominator and it can't equal 0, I can still get a critical number of it. So let's try it out. So let's type this one in first. Type this one into your calculator. Throw it on the floor. Then type it into your calculator. It jumped?
Yeah.
Crazy calculator. I'm going to post this. That was a picture. I'm assuming everyone doesn't have their textbook on them.
I do it today. I'm just going to go back. I searched it up.
So what I want you to do, if you do have your textbook so you can see in front of your face, is turn to page 290. So these are the functions that sit in front of you, and we'll talk about where critical numbers hit. So this was on page 290. It gave examples. So if you look here, this function that's given to you in figure 10, if you look, all of these actually have restricted domains. Their domains are stopping, correct? So we have between 0 and 3 pi over 2 for this one for our domain. Square brackets so that there's the dots on the end are closed. Make sure you're paying attention on your phone. So there's a closed dot here and a closed dot here. We agree? It's because we have square brackets on our domain. So if they restrict our domain, they could give us a degree 4 function and restrict the domain so you only have a little piece of it. They can do that as well, right? So when they restrict the domain here, this is continuous from 0 to 3 pi over 2. It also has an absolute, and they talk about absolute maxes and mins all the time. There's either absolute or there's local. Absolute means it's the absolute highest it could go and the absolute lowest it can go. Okay? So for example, this one has an absolute maximum at 0, 1, and it has an absolute minimum at pi and negative a half, and this here is just an endpoint. It's neither a max nor a min, it's just floating in the inside. Okay? And there's no local max or mins here. Now, something to note, you can have a local max or a min if it's not an endpoint. So an example would be if I did something like this. So my endpoints here would be my absolute min and my absolute max. We agree? Because they're the highest they could go. So if I restrict my domain, my endpoints can be absolute maxes and absolute mins, but they can't be locals. So they're either the highest they go or the lowest they go, or they're just endpoints. Okay? But these mins and max in the middle, this is a local max and this is a local min because they're not the absolute highest or lowest I go. Okay? This graph up here, though, that was an absolute max, that first endpoint. Here's an absolute min, my minimum, and then this is just either an endpoint or an absolute max or a min. Is this one absolute? That endpoint? No, it's in the middle, correct? So it's just an endpoint. So your endpoints can either be absolutes or nothing, just an endpoint. Does that make sense? When they restrict their domain. So this one here, they restricted the domain between -1 and 3, and it's a round bracket. Why is it round brackets? It's not a coordinate. It's not equal to, there's open dots. We agree? So you have to watch yourself when it's the open dotted domains, because often people will be drawn to them as a coordinate. It's not a coordinate because the word domain beside it, that just means they're not equal to, right? It's also continuous from -1 to 3. It has an absolute maximum at 0, 1. And it has an absolute minimum at 2 and -7. It has a local min at 0 and 1, and a local max at 2 and -7. So locals are all of them. Yeah.
So if it's like a function that isn't restricted by the domain, would there be like, if it was like a cube or a cubic function or something?
They'll always be local.
Okay, so then there would be no absolute.
Right. Because you know a cubic function carries on up and down forever. Yeah. So they would have to restrict the domain of a cubic in order for there to be an absolute, which they do. They sometimes restrict the domain and then sometimes they don't. Okay. This one here is a rational function. It is actually straight. It's just in a textbook that's curved, so my phone made it curved. But imagine that as straight x-axis. Okay. So the domain is from -1 to 4, round bracket of -1, because it's going to get closer and closer and closer to -1, but it's not going to touch it, correct? Because it's a rational function. It's continuous from -1 to 4. It has no absolute maximum value. Why? Because that's going to keep going up and up and up for life, correct? This actually has an arrow on it. And it has no local minimum, but it does have an absolute minimum. It's this curved one that's supposed to be straight at 4 and -1. Okay, these ones down here are a little different because they're not always continuous from the domain. So here the domain is from 0 to e, and it's continuous from 0 to e. There's no absolute maximum value. Why? Because the absolute maximum is actually an open dot. So what is the value if it's an open dot? I don't know. It gets extremely, extremely, extremely close to whatever e is when you plug it into that value. But it doesn't actually give you e. So when your endpoint is open, there's no absolute. And there's no absolute minimum because this baby keeps going on for life. There's no local max. There's no local min. This one here is from 0 to 6. And it's continuous from 0 to 6, except at x equals 2, which means it's not continuous, so I don't know why this is continuous. It has an absolute max at 2 and 6, and an absolute min at 6 and -2. It has a local min at 2 and 6, and a local max at a min at 5 and or 1 and 0. This one here is a minimum, but it's local. Okay, and then this one here, it's continuous except, which I don't like that word because it's not continuous. It has an absolute max at 2 and -3 and 2, 3, and it doesn't have a min. Why? It's no, there's no absolute. Okay, so we'll go back to here. We type this one in. What was our original again? I can't remember. 4 minus root. So 4 minus square root x. Is there going to be a max or a min here?
No, not an absolute.
Is it closed or open on the original? Is it closed or open on the original?
Isn't that open?
No, because it can be greater than or equal to 0, right? It's not in the, it's
on
not,
the other.
yes. So my point of saying to you is that the non-permissible values can still be critical numbers on the original, correct? So what's the critical number on this original one? 0, isn't it? Because the maximum happens at 0, does it not? So even though down here it's a problem on my first derivative, it doesn't exist on my first derivative, that is true. So if I went to draw my first derivative graph, I would have an open dot at 0. I absolutely would. But on my original, I would have, I'd say my critical number would be x equals, technically is x can't equal 0, but that still is a critical number on this one at x equals 0. Your non-permissible values still are critical numbers of your original. So don't let them throw you off. Just because they're not a non-permissible value, just because they are a non-permissible value of your first derivative, doesn't mean they're not a critical number of your original, because it was still fine to have 0. And why was it fine to have 0? Because this isn't in a denominator, right? So it's just x is greater than or equal to 0. But you also could use your radical rules as well. This is a radical graph that's been reflected down, like it's reflected in the y-axis and moved 4 up. So I know that this graph is at 0 and 4, and it's reflected down. Just based off of your 30-1. Yeah, it's curved this way. Just off your 30-1 knowledge, though, you would know this is the highest it could go, whether you drew it wrong or not. And you're me. Because this is the highest it could go, it goes up to 4. Because remember your radical graphs from 30-1, your parent functions? It's at 0, 0, and it goes up and to the right, correct? And now it's just going to be down and to the left, and that's why it curves the way it's supposed to and not the way I did it, because it doesn't make any sense. But it curves down and to the left, but it also moved up 4. So it's like this. Right? So you can still use your knowledge from 30-1 to help you out. Okay, so the critical number for that one is x equals 0. Number 4, what if I give you this thing? You're going to do x plus sine x. F of x equals x plus sine x. Now, the trig, you pray and hope they always give you some sort of restricted domain or keep on for life, right? So they're restricting it from 0 to pi. If they don't restrict it from 0 to pi, you would have to give general solution, is all. Because you'd have critical numbers that would keep happening every so often, right? So I want you to find the first derivative of it and then try and solve it. So we're going to get f prime of x equals 1 plus the derivative of sine x is cos x. And then I set it equal to 0 to get my critical numbers. Because I'm setting, why am I setting it equal to 0? Because the horizontal tangent has a slope of 0. So I'm plugging in 0. And horizontal tangents occur when I have max, mins, points of inflection. So those are my critical numbers. Okay, so I'm going to subtract 1. And I'm going to get where cos x equals -1. Calgary Stampede. So cos is x. So it's -1 is here, which is at where? Pi. Is it inclusive? Yes. If it wasn't inclusive, if it was round bracket, what would I say? There are no critical numbers, so you wouldn't have any. So you for sure wouldn't have any maxes or mins, because could the graph have maxes and mins? Absolutely. But are there max and mins in that domain? No. Right? So some people think that that means that it doesn't have any max and mins. It can absolutely have max and mins, but the restricted domain doesn't. So the critical number is that x equals pi. Now please type them into your calculator if you haven't done that yet. And make sure your mode is in radians. And you're going to have to change your window to something that's actually going to work. So we have x minus plus? I'm like, I can't remember. X plus sine x. And then 1 minus cos. Crap. You know what? You guys are very lucky that you're in the brain wave of only moving one direction. My brain will try and derivative and take off derivatives all the time. Because once you get to implicit, you're going to have to remember that when you're going and when you go to do integrals, we go this way, sine is positive, right? When we go this way, it's still positive, but you have to watch yourself. So like if I had a negative sign and I went to do the antiderivative of that, the answer would actually be cos. Because you're working backwards.
Is that just like pressing it or is it
It's just knowing that cos, the derivative of cos is negative sine. So now if I have negative sine, work it back to negative cos. Or if I have sine and I work it back, it's negative cos.
You said we're getting the inverses, right? But
Yes.
not
But not the basic traits. Yeah. And right now you have the luxury of not thinking the other way. My brain sometimes tries to do the other way.
And it's also time change.
Sure. Yeah, that 1 hour really wrecked me. It's so bad. What about all the rest of the days that I do this? Time change.
Time change. It's always the time.
Okay. No. This has nothing to do with this. Okay, so we have 31 days left.
We should adjust it.
31.
Yeah.
31 for concept.
Take this off 30.
We'll do it.
No. Okay, so we're doing pi divided by 2. And we press graph. And if you look here, red is the first derivative. I'm really good. So here is where my critical number exists in my first derivative, we agree? Which is where, what's going to happen on this one? The maximum. Now this is also something. On my first derivative, this, people will tell me it's decreasing. Yes, my first derivative is decreasing, but where is this part? It's above the actual x-axis, so on the original, my graph is increasing. They'll make you graph graphs from graphs. So they'll give you like a second derivative graph and make you get back to the first. Or they'll give you a first and get you the second. You'll practice it enough, it's not hard. That's not going to be when you get stuck on. Huh? No, that's normal too. All right. So these were decent derivatives. Number 5. Okay, I want to do the derivative of this one. Try these out. No, I'm not being facetious. I literally don't know.
Okay.
What? Sorry. Try again.
Okay, I mean, like, will most of the chain within a quotient thing be so ugly that we'll probably just end up doing the long way anyways?
Chain within a quotient.
Like the long of both sides, whatever you call it, logarithm.
No, like you're gonna do that normally. You're not gonna choose
No, not
that.
that one. I mean, like, I mean, like, ones that have a chain.
They'll be blatantly obvious that they're a logarithmic
Yeah, chain
differentiation.
within, like, a quotient.
Within, yeah. Well, if you had a chain,
Not just that.
if you had this divided by that, you'd still do this normally. You're not going to do logarithmic differentiation.
Can you?
No, it won't do the same thing.
They won't.
It won't get you the answer that's in the multiple choice, so.
So
Because
let's see if it can be correct.
Technically, but they're not going to accept it, like on a,
Multiple choice.
because it won't match a multiple choice, and you won't be doing it the proper way, technically.
But have we
If it was
made
a short answer, that would be correct.
No, because they would say solve by logarithmic differentiation. If not, they're assuming you're not. Yeah. Yeah. So they don't want you doing 6 if it's that divided by that. They do not want you doing logarithmic differentiation. They want you to do quotient rule with
No, that one
change.
makes sense. I meant like if it was over something ugly. Like if it was that on the top and then it was like.
That's different. That's logarithmic. And they'll be
That's what I was asking.
No, I said to you if they just took this one
Uh-huh.
and put it underneath that one. That's a plain quotient rule. You can't do that as logarithmic.
Okay.
Because it's not going to match answers, and the only way you do logarithmic differentiation is if it says using logarithmic differentiation.
I'd also see that in the multiple choice.
No, but it won't match.
Wouldn't
Like
it-
you'll do logarithmic and you get an answer, it will not be an answer in the multiple choice. You'll waste your time.
Okay. Would it still be considered a chain? Because if you had like this, you don't you still have to go there in front and you go to prime and G prime?
Yeah. All right. So here we're going to take an x out. We're left with x minus 2, x minus 1 squared. So even though on the first derivative this is going to be an asymptote, correct? It's still a critical number of the first. Now a critical number on the first could be an asymptote. Like just because, so if I get x equals 0, 2, and 1, I told you that that's where max, mins, and points of inflection occur, correct? Because we've only talked about polynomials. But you also do know that if it's a rational, it's going to have an asymptote right off the bat. Like you know that because of 30-1. So these critical numbers, 0, 2, and 1, when it's a rational function, could be a critical number. It could be for a max, a min, a point of inflection, or an asymptote. So if I go back here, what is 1? It's a vertical asymptote. Because it didn't cancel off, it's not a point discontinuity, which is called, not points discontinuity. They're called jump asymptotes, or what's the other one? It's not jump. Why did it leave? It's because we do points discontinuity in 30-1 all the time, and then they call it something different in calculus. I told you guys this already.
I guess we
We'll never know.
You'll know because when you see it, it literally just doesn't call it a point of discontinuity. It just asks for removable discontinuity. Yes?
I was thinking eraser.
No. So this is a vertical asymptote, which is true, but still, this is a critical number. Okay. And when we go to do this one, we have f, we have g, we have f prime, which is going to be 2x plus 3 to the 1 times 1, technically, which is just 2x plus 3. My g prime is going to be 2/3 x minus 1 to the negative 1/3 times 1, which is just 2/3 x minus 1 to the negative 1/3. Now I know that if I have chain rules embedded in my product or my quotient, I'm going to be able to take out GCFs. I also know that when I take out a GCF, the smallest fraction exponent, that one will go away, the other one will become 1 every single time. Every single time. That has not changed. Even though we're using 2/3 instead of and 1/3 instead of a half, it's still going to get me 1. So I picked this one specifically to prove that point. So we do f prime of x equals, we get f, which is x plus 3 squared, times g prime, which is 2/3, times x minus 1 to the negative 1/3, plus So f times g, which is x minus 1 to the 2/3 times f prime, which is 2, and then x plus 3. So I know that I could take out a 2/3, or if I really wanted to, I could just take out a third, then take out the 2. It doesn't matter. But I'm going to take the 2/3 out because I want the 3 to drop to the bottom. So I'm going to take out a 2/3 as my GCF. I'm also going to take out one of the x plus 3's, and then I'm going to take out my smallest exponent, which is negative, x minus 1 to the negative 1/3. And I'm going to write what's left over. So if I take a 2/3 out of 2/3, it's gone. If I take an x to the negative 1 to the negative 1/3 out, it's gone. X plus 3, I take one of them out, I'm still left with x plus 3. Then plus sign. What's 2 if I take out 2/3? 2 divided by 2/3 is 2 times 3/2, which is 3. So I'm left with 3. The x plus 3 leaves. And then I have an x minus, just proving a point, but it will always become 1. I'm proving it again. So if we do x minus 1 to the 2/3, and I divide it by x minus 1 to the negative 1/3, it's going to be x minus 1. And what do I do with the exponents? I subtract them when I divide by the same base. 2/3 minus a minus 1/3 is actually 2/3 plus 1/3, which is actually 3/3, which is actually 1. It came out a 1 again. Every single time you chain rule a fraction, 1 will go away and 1 will become a 1. If you're like, when will it never? It will always happen because you're chain ruling it. And when you're chain ruling it, you're knocking that one down by enough that when it joins the other one, they'll become a 1 every single time. Because why? You're taking 1 off. Correct? You're taking 1 off. When you subtract by 1, you actually subtract a negative, you actually add 1. So it'll work out.
Value into this one later once you get your answer and then check it with like the using the original and then the dy dx.
To check them, you can always do that, yeah. If you have a calculator.
Is there any ones where you can't?
Well, it's just in the non-calculator section of your AP exam. You don't have it, so you can't use it.
I'm planning on failing that.
You will not fail that. So then I get an x minus 1 to the 3rd on the bottom and a 3 on the bottom. And then on the top I'm going to get, so I'm going to get x and 3x is 4x, and then the 3's cancel. Oh boy. You have to rewrite. So I'm going to get 8x, x plus 3 over 3, and then it's going to be the cube root of x minus 1. It might look like that.
I did it right, or I did it wrong right off the bat because my brain read 3 over 2.
Oh. So if it's like that, if it's a 3 over 2, you'd end up taking 1 off. It might not always be a 1. It's always when the fraction is less than 1, right? That's opposite to a 1.
Oh. Now we just don't
Yes.
Like how, what point would we have to simplify to? Like do we have to get like that version right there?
Yeah. Yeah. So the critical numbers we can now get from this, we have x equals 0, negative 3, and 1. So the people who struggle with derivatives struggle with this unit because if you can't find the derivative, you can't do this stuff. But you have to remember that they don't give you the craziest derivatives in this unit because you're just trying to draw something like this is the hardest it gets, is one like this. It's not going to be one where there's like a chain embedded in a blah, trig, blah stuff. Yeah, chain, trig, power, product, yeah. No.
You said when we're expanding, we're not simplifying anymore, so why did you not do
Because they're just like, they're both like terms you put them together. Like you could leave them separate, but they won't. They'll put them together because the 2 and an 8, 2 and a 4 makes an 8. So right now, this isn't actually as simple as if I put 2 and 4 made it an 8x. Like this is less numbers, so it is simpler.
How good do people usually do on the test? Is the average usually